I'm Brett McKim. I'm a PhD student at the University of Exeter, and this is some work on the Longwave Clearsky feedback and how it depends on surface temperature and relative humidity. My advisors are Nader Jivanji at GFDL and Jeff Vallis at the University of Exeter. So, what is the Longwave Clearsky feedback, and why do we study it? We study the Longwave Clearsky feedback because it dominates the climate sensitivity. So if we need to sum up the Planck, lapse rate, and water vapor feedbacks, those have the greatest contributions overall to the equilibrium climate sensitivity. And this paper by Bjorn Stevens and Sandrine Bonny in Physics Today have a nice figure related to this point. Furthermore, GCMs agree on long-wave Clearsky feedback. And so if you look here at this regression of Clearsky OLR and surface temperature, the slope of this line gives you the long-wave Clearsky feedback. And you can see that among all these CMIP5 members, the slopes are very similar. They're about 1.9 watts per meter squared per Kelvin, and they vary by about 5% from each other. And this is in light of the fact that the humidity fields and the temperature fields of these models are different, and yet they're still showing the same feedback value. And we should understand why that's the case. So the results I'm going to show today come from a paper recently published in GRL, which you can also find on my website. And the key points to take away are that a parameter sweep shows that the long-wave Clearsky feedback exhibits a canonical value of about 2 watts per meter squared per Kelvin. However, deviations from this value can occur at high temperatures, like in the tropics. And these two insights can give us, can help us to interpret a number of results in the literature. And so we're going to try to reproduce this roughly 2 watts per meter squared per Kelvin seen in the GCMs in a single column model. So we're using a column model with line-by-line radiative transfer and moist adiabatic physics. So that means to specify our column, we just need to specify the surface temperature on the y-axis and the vertical profile relative humidity on the x-axis. We've just assumed that it's a uniform vertical profile. And then because we have a moist adiabatic atmosphere, that determines the temperature profile. So what we can do is calculate the feedback for these columns and then plot that as a function of surface temperature and relative humidity. And so the feedback is denoted by the colors and the contours. And so the first thing that we'll note from this plot is just how much this 2.2 contour seems to dominate. So at the lower half of this plot, this contour represents the largest area here. So what that means is that if you were to move or to change your surface temperature or relative humidity in this region, your feedback would stay roughly the same. And so this helps us to interpret these results in the GCMs, which show that this remarkable agreement. It's because that when you're in this stable regime here, your feedback just isn't changing that much. And so we shouldn't be surprised that the GCMs show remarkable agreement between each other. That being said, there are deviations from this canonical value in the upper portion of the graph. And that's because as you get warmer, your water vapor window is closing due to enhanced continuum absorption. And so that means that there is now a temperature and humidity dependence of your feedback. And so when you move around in parameter space, you're now changing the feedback. And so this helps to explain why the GCMs were finding slightly lower values of about 1.9 watts per meter squared per Kelvin. It's because half the globe is in this more stable regime, and then half the globe is in this more sensitive regime, where now it matters what humidity and what temperature you're at. And that's because the tropics occupy about half the area of the globe. This phase space also tells us a little bit about the enhanced climate sensitivity or nonlinear climate sensitivity seen in other works. So in this other work, for example, by Jonah Block-Johnson, they attribute the increased climate sensitivity with warming to a decreasing feedback parameter, namely the Longwave Clearsky feedback parameter. And so we can interpret that with this graph by showing how this box, which represents the Earth-like parameter space, if you were to move this square up, then you're now shifting more of your planet into this sensitive regime where the humidity dependence matters and where generally your feedback parameter is now decreasing with surface temperature. And so this is consistent with the picture shown by Jonah Block-Johnson and colleagues. And the final thing we can offer some insight on is this notion of subtropical radiator fins that Ray Pierre-Humbert introduced in 1995, where he talked about how the subtropical regions are relatively warm yet dry, and so they are radiatively stable and tend to stabilize the tropics, whereas the deep tropics are relatively warm and moist, and so they tend to destabilize the tropics. We can interpret this more simply as just the fact that the Clearsky feedback parameter changes as a function of humidity in this part of the parameter space. And so, for more info on this project, you can check out the paper, which is available at my website. We also do some work on the effect of clouds. And if you're interested in a longer talk available on related work, check out the 13th ECS Virtual Symposium, which you can find on YouTube, where Nader Jivanji gives a great talk. Thanks for listening.